Hello everyone, welcome back to the channel. So today we will be starting uh, starting solving questions from this CP-31 sheet by the TLE Eliminators. And yes, we will start from 1800 level difficulty, and I hope to complete all of these problems and upload their solutions on the channel as well. So stay tuned. Okay, so I have already discussed the first question. I have already discussed the first question on the channel, which is gerrymandering. You can definitely try to solve it and take a look at the solution if you are not able to solve it. Yes, it is a pretty nice problem based upon the DP. Okay, so today we are going to see this question called Rendez-vous de Marian et Robin. I don't know what that means, but yeah, let us take a look at the question. Okay, so Marian sold her last wear at the market at the same time Robin finished training at the Major Oak. They couldn't wait to meet, so they both start without delay. So there are timestamps below the video if you are already familiar with the problem statement and understood it thoroughly. I recommend you to directly skipping to the solution part of the video. So the travel network is represented as n vertices numbered from 1 to n and m edges. The ith edge connects vertices ui and vi and takes wi seconds to travel. So all wi are even. So this is one of the important parts of the problem. So Marian stands, or whatever Marian stands at vertex 1, which is market where she sold her last wear, and Robin starts at vertex N, which is Major Oak, where he finished his training. So in addition, each of the n vertices each has a single horse available. Okay, so both Marian and Robin are capable riders and could mount horses in no time. Means in 0 seconds. So travel times are halved when riding. Once mounted, a horse lasts the remainder of the travel. Meeting must take place on a vertex, not on edge. So either could choose to wait on any vertex. So output the earliest time a Robin and Marian can meet. So if the vertices are numbered 1 to n, and if 1 and n are disconnected, they are part of the different connected components of the graph, then we have to output -1, as they won't be able to meet as they are traveling through the or on the edges, right? So input parameters are quite standard in mh, all up to 2 into 10 to the power of 5, and notice that time limit per test is 5 seconds. Okay, so I actually struggled with the time limit, but anyways, yeah, I found the solution. So then, so standard uh, tree, sorry, standard graph input. So n is the number of vertices, m is the number of edges, h is the number of the places where horse is available, and second line of each test case depicts those number where the horse is available. Okay, so let us take a look at the first sample test case, first, second and fifth. So they will give you pretty much idea of everything, right? So okay, so let me clearly demarcate the test cases, and one more test case that we have at our disposal is fifth one. So this is kind of tricky test case, so just make it quite bigger, get it in the row or queue, whatever it is. So here there are only two vertices. This is the first vertex and this is the second vertex. There is one edge joining which has weight 10, and horse is available at the first position. So there is horse available here. So minimum time so that they both reach will be 5, right? So Marian will ride horse here or mount horse here and travel to the 2 within the time 10 by 2, and Robin will just wait here. Okay, makes sense. So in this test case answer should be 5, which is indeed 5. So in second test case we notice that there are 3 vertices. So here Marian will be there, here is the node 3 2, and here it is 3. Here Robin will be there, here Marian will be there, and horses are at 2 and 3, H and H, but only 1 and 2 is connected, okay, with the weight 10. So Robin is here and Marian is here, so they won't be able to meet at any node, right? So for this test case our oh, our answer will be -1. Make sense? Yes. So they won't be able to meet because they are in different connected components. So is it -1? Yes, it actually is. Now this fifth test case is kind of trickier, so let's take a look. So here n is equal to 3 and number of edges is 2. So 1 2 3. 1 2 is connected like this 4, and 1 3 is connected like 16. So 16 weight. So there is only one horse available at 2, right? So here Marian will be there and here Robin will be there. So you'll think that 16 should be answer right here. So you'll think first thought in your mind will be like 16 will be answer, Robin will go from here to here, or Marian will go from here to here, and they'll meet in this time of 16. But that is not the case. What will happen actually here is that Marian will wait, Marian won't go anywhere, but Robin will go here with spending 4 seconds of time or 4 units of time. He'll mount the horse here and then he'll follow this journey. Then how much will it cost him? How much time will it cost him? So 16 plus 4 by 2, right? So which is 10. So we are getting 14 units of time, so which is less than 16, right? 14 is less than 16. So in this case our ideal answer would be 14. Okay, so that is the whole point of the problem. Okay, so first intuition that comes to your mind, when you read this problem is Dijkstra's algorithm. I am bad at pronunciation sometime, so Dijkstra's algorithm. Okay, anyways. Okay, so why does this come to your mind? Because what you will do is that you will start Dijkstra from the first vertex, and you will run second Dijkstra or same Dijkstra on the vertex n. So source will vary from 1 and n. Okay, not vary from 1 and n, we have to just run it 2 times. Okay, so everybody knows that complexity of Dijkstra algorithm is like e log v, v plus e log v, right? V plus e log v, if I remember it correctly. So e is the number of edges and v is the number of vertices. Okay, so here it is kind of n log n, right? So this will definitely pass our time limit because it is big enough, right? It is 5 seconds and our n is up to 2 into 10 to the power of 5. Yep, makes sense. So this is the time complexity of the Dijkstra's algorithm, O of v plus big O of, or theta of, you can say, v plus e log v. So it is the feasible option to get towards the answer if we can. Okay, so I will run Dijkstra starting from the first vertex and I'll note. So Dijkstra is single source shortest path algorithm, right? So it will return the distance of the shortest distance. So it will return the shortest distance from a source to every other vertex, right? To every other vertex. right? If you don't know how the Dijkstra or this algorithm works, I definitely recommend you to search it up on Google, or learn it from CP algorithm or some YouTube tutorial. So it is a fairly simple algorithm. You don't need proof as in such for competitive programming, at least at my level. I don't know about the higher levels, but yeah, till now I didn't need the proof of it, although I know the proof. But yeah, you can explore it on the CP algorithms. Yes. So we will run Dijkstra from the source 1, and it will return us the shortest distance to every other vertex, and we'll do the same for the n as well. So it will also return shortest distance from the vertex n to every other vertex. Okay, so suppose my distance 1 array is like distance from source 1 to every other vertex. So 1, 2, 3, 4, these are the vertices. Okay, so on up to n. So distance from 1 to 1 will be 0. From 1 to 2, let us suppose it is 5, here it is 2, here it is 10, and so on up to some value val. Okay, and if distance 2, so we are going to consider the mounting horses and then riding as well, right? So we have to consider that as well. So distance 2 array is like, suppose val 2. Okay, so this is val 1, this is val 2, and okay, val 2 will be 0. That's the thing. And so value of 2 will be 0. Okay, so what is happening? So value of 2 will be 0 because we are starting Dijkstra from n in the second part, right? So if these are the distances, so what will be my answer? What will be my answer? Will it be like, so at 1, this Robin, okay, Marian is starting Dijkstra from 1, Marian, and our Robin is starting Dijkstra from n, right? So at 1, suppose Marian is arriving at 0, and at 1 Robin is arriving at 1. So when will they meet? They will meet at the first second, right, or first unit of time. What about if they meet at second node? So 5, right? My answer will be 5 if they meet at the second node. What about the third node? It will be 3, right? Because we have to take maximum of these both. We have to take maximum of these both, right? So if they determine to uh, uh, meet at the fourth node, uh, uh, my answer will be like 10, right? So answer will be minimum of maximum of dist 1 of I and distance 2 of I, right? So this will be my answer, right? Minimum of minimum over all I, right? So for all I, this will be my answer. So that is basically the point of the solution, the point of applying Dijkstra here. So, and one more thing to notice here is that, so if you apply Dijkstra's algorithm here, then you'll get that you start Dijkstra for the okay, Marian is at 1, right? So sorry, Marian is at 1 and Robin is at 3, right? uh, yes, Robin is at 3, so Marian is at 1. So if you start Dijkstra from here, then you notice that uh, so you notice that your 16 will be the minimum distance here, right? But we want 14. Why we want 14? Because why we can achieve 14 is that we have horse available at the second node, right? So how can we account for the horse? So that is where our comes in. So the thing that comes in here is that, so the thing that comes here is that, so this was the graph, right? 1 3, this is 4, and this is 16, right? So Marian starts from here and Robin starts from here. And now what Marian will do is that Marian will go here, mount a horse, ride it till the third node to meet the Robin, right? So in my Dijkstra's algorithm, I'll make one modification, and that modification will be that, so remember that if we have relaxed edges, so remember, if we have relaxed edges using any of the vertex in the Dijkstra's algorithm, we don't push into the priority queue, right? So if I have relaxed my edges from this one, so if I have relaxed my edges starting from 1, then if I again encounter 1, I won't add it to the priority queue, right? But here the case is different. How is the case different here? Because I have to maintain two states for any vertex, state 1 and state 2. What are these two states? The two states are that I have neutralized the edges, or neutralized the distances of vertices. State 1 is that I have neutralized the vertices starting when I was walking, not on the horse. I was walking and I was not on the horse. So state 1 is like you start from 1 and go till here and relax this to 16, right? Because it was at infinity first, and you'll relax it to the 16 while walking. And now if you go here, if you pick up the horse, and when you come back to the 1, now you have horse. Now you'll neutralize the edges based on your state 2, that I will neutralize edges or the distances of the nodes while riding. Make sense? Yes, it absolutely does. So my my distances, dist 1 of I and dist 2 of I will actually be pair of LL comma LL, long comma long. So what will they store? They will basically store this first value, will store that minimum distance while walking, right? Minimum distance, like you came there by walking, right? So, and this will store that what is the minimum distance if you came there by horse, right? By riding. Okay, these are my two parameters for this distance array. And yes, that is basically the whole solution. There is nothing more fancy here, just we have to modify the Dijkstra's algorithm. So yes, let us take a look at the solution code. So code walkthrough. So let's go. And one more important part here. So if you like create priority queue, so this is the key takeaway from this solution. So key takeaway, if you like uh, declare priority queue of something like pair pair of ll comma ll comma bool, and basically this thing, right? This thing pq, priority queue. If you initialize it this way and try to access its elements frequently, like you do element which will be auto element which will be pq dot top, and if you like do element dot first and you'll do dot first dot second. Now these are the operations that are not access efficient, right? To be access efficient you have to use tuple. Okay, you have to use tuple of ll comma ll comma bool tpl. Okay, so instead of doing this thing I have to use like this. So this way I can optimize my code, right? This way I can optimize my code, and like this will provide much faster accesses, right? It is aligned in the memory in such way, right? So much faster accesses using tuple. Okay, so that is the whole point of it, and this is the key takeaway. So yes, I have type def this thing to the TPL to save the typing work, and yep. So let us head towards the main section first, and this is the input part, standard input part, and I have discussed what these two arrays will do. And this is like visited. This will also be the pair of bool comma bool, right? So this first argument will denote if it was visited by walking, and this second argument will denote if it was visited by horse while riding, right? And you will call Dijkastra from 1 and from n, and finally this is the discussed answer calculating part. So let us head to our Dijkastra's code. So Dijkastra, what do we do first of all in Dijkastra? We just mark the distance of that node. We just mark the distance of that node to be 0, right? Starting node, starting vertex. So if it is like there is already horse there, then you have visited it by walking and by horse as well, right? So that's why dot first is equal to 0, dot second is equal to 0 as well, else you have just visited it by walking. Okay, so that's the thing, and this is our priority queue. And you know why this greater TPL is there, right? So we want to access the minimum distance node, right? So we have to perform the relaxation in the every iteration of the Dijkstra's algorithm. We have to perform the relaxation starting from the nearest node. Okay, that's the principle of Dijkstra's algorithm, and this is achieving the same thing. So if I do pq.top here, it will give me the minimum distance node. Okay, makes sense? Yes, it absolutely does. So, and the second thing, you know that you have to push the neutralize the edges before this while loop related to this source vertex, right? So you will just fill a priority queue based upon if there is horse or not. So basically this bool, this third parameter bool, is that you are having horse or not, right? You are having horse or not. Okay, so if you are having horse, then your distance will be halved. It will be divided by 2, and if you don't have horse, it will be the same element dot second, but you are checking the node at which you will step, right? So at which you will step, and if that has a horse, then you will mark you will push the element or emplace the element which is like having horse in it. Okay, and this is self-explanatory as well as this one. And okay, so visited of vertex dot second is true, else visited of vertex dot first is true. So this is basically if our vertex is having the horse or not, right? So that's the simple thing. And yes, and this is also the most important part of the solution, right? So if you have already visited the node with the horse, and you are also having the horse now, right? So basically it is the redundant, right? It is the redundant part of our solution if we check those nodes as well, because this node is visited, if this node is visited by the horse, because dot second is true, and now we are having the horse and we will perform the relaxations, that is redundant, right? We don't want to do that. And same is the case with the walking scenario, right? And in this both the cases we will continue. And yes, this is the relaxation part, which is basically same as this part. Okay, nothing more fancy there. Okay, so finally, if horse is true, we will mark that node's second part as true, otherwise the first part as true. These are some debugging steps I have added, and yes, I have popped the element in the beginning itself, so no need to pop it after the for loop. Okay, so this is basically the whole solution. I hope you enjoyed solving the problem. Okay, so and listening to the solution as well. If you solved it on your own, kudos, congratulations. And yes, and still if you listen to the solution even after solving it, I'm really grateful towards you. So yep, thank you. So be sure to recommend if there are any suggestions regarding the way I explain the solutions, or anything that you can feel that I can improve. Your suggestions mean a lot to me, and I will definitely consider them. Okay, so thank you for watching the video again, and I will continue this TLE Eliminators CP sheet till the end, right? Like so. Like I will cover all these 31 problems, then I will hop to 1900 as well. I will do 1700 as well as the 1600. Okay, I want to do many things, right? I want to do as much as I can. So let's see how it goes. So thank you again for watching the video. If you learned something new, through the solution, basically if you didn't know this priority queue part, right? So if you didn't know that tuples have the faster memory accesses compared to this pair structures, if you found it new, or found anything new in this solution, found something interesting, make sure to like the video and staying subscribed to the channel. And yep, we are a community of almost 100 people. We are real close to it, and thank you for the support that you have shown till and will show further. Thank you. See you again.